So this talk is called Relativity Principle combined with Quantum Superposition Principle. This video is a bit different to my usual videos. Most of the time I criticise what is said about Einstein's relativity. This time I'm going to try to solve a problem in relativity. The proposal is think of the relativity principle in a different way than it's usually stated and combine it with the quantum superposition principle. The easiest way to illustrate quantum superposition is with Schrodinger's cat. Schrodinger's cat is a well-known paradox in physics, in the quantum mechanics. It's a thought experiment that illustrates a paradox of quantum superposition. In the thought experiment, a hypothetical cat may be considered simultaneously both dead and alive as a result of its fate being linked to a random subatomic event that may or may not occur. The cat, a flask of poison and a radioactive source are placed in a sealed box. If an internal monitor, i.e. Geiger counter, detects radioactivity, then a single atom decaying the glass is shattered, releasing the poison which kills the cat. The Copenhagen interpretation of quantum mechanics implies that after a while the cat is simultaneously alive and dead, yet when one looks in the box one sees the cat either alive or dead, not both alive and dead. This poses the question of when exactly quantum superposition ends and reality resolves into one possibility or the other. So, as I'm pointing out, the cat exists in a state of being both alive and dead until it's observed. And once observed, it becomes one of those states. Either you observe it as dead or you observe it as alive. You don't observe it as being both dead and alive at the same time. So that's the point. It's not until observation do you know what state an object it is in. What's in the box you don't know until you look. And since cat is not a quantum particle, going to call it now on just superposition principle. So now on to the relativity principle. Now this is according to Einstein Online as to what the relativity principle is. Now people do say lots of other different things, but for the sake of this video we're going to go by what this relativity principle is supposed to be. The basic principle of special relativity for two observers moving relative to each other with constant relative velocity, more specifically for two inertial observers. The laws of physics are the same, and you can read the rest of it. So now I'm going to deal with the relativity principle in a slightly different way than it's usually presented. Given two spaceships moving at constant velocity relative to each other, can't tell who is moving in an absolute sense. In this idealized situation, have nothing that can plot their motion relative to other than plot motion relative to each other. The only motion being considered is of the spaceships relative to each other. So for an inertial situation such as this, given from frame of A observes B moving at constant velocity v to the right, then from frame of B would say A was moving at constant velocity to the left. And this is it shown from frame of B would say A was moving at constant velocity v to the left. That's the relativity of velocity, and I'm ignoring the positive and negative signs that would normally be used to indicate direction. So for this situation, don't know who is moving in an absolute sense. Instead, we got a relative sense. Each could claim themselves at rest with the other as moving. So A can claim itself as being I'm at rest and B is moving, and B can claim I'm at rest and it's A that's moving. Now by special relativity there is time dilation, and that's usually shortened to saying moving clocks run slow. Thus, since each spaceship can believe the other spaceship is moving, they can say the other ship's clock runs slow, and that is symmetric time dilation. A says the B clock is slower and B says the A clock is slower, and many critics of relativity say this does not make sense. So instead of that, let's consider the following situation. For an inertial situation like this of spaceship A and B initially at rest relative to each other, and later they're moving relative to each other. So the situation of A and B being at rest, and that would be an inertial situation, is then followed by this inertial situation where A and B are moving at constant velocity relative to each other. A observes B moving at constant velocity v to the right, and B observes A as moving at constant velocity v to the left. So what we're doing is getting from one situation where they're at rest to this other situation where they're moving at constant velocity relative to each other. Now there has to be non-inertial motion involved, and either A or B or both of them have had to experience acceleration, and they were not always in an inertial situation. If B underwent acceleration and A stayed in inertial state of rest, then when A says B clock runs slower, B would agree that his clock was slower because would have felt acceleration and now not in an inertial state. Similarly, if A accelerated and not B, then both would agree that A clock was slower. Thus we then get asymmetric time dilation. It, however, does not help us for the following situation where A and B are unaware of any acceleration and move at constant velocity v relative to each other, which would then give symmetric time dilation. A observes B moving at constant velocity v to the right, and B observes A as moving at constant velocity v to the left. So this is why we should now bring in the superposition principle. The superposition principle for the cat: don't know if the cat is alive or dead until make the observation of looking in the box. Similarly, for two spaceships, if don't know which clock is really slower, have to make the observation to find out. When have symmetric time dilation, it just means no observation being made. When an observation is made, then it collapses to being asymmetric time dilation. A observes B moving at constant velocity to the right, and B observes A moving at constant velocity v to the left. The observation tells us when it's made what spaceship has not been fully inertial in its motion. Schrodinger's cat, both dead and alive until observation, then collapses to one state, either dead or alive, not both states. Spaceships both clock slower until observation, then it collapses to only one clock slower, not both clocks slower. The cat being both alive and dead is unobserved. The clocks being both slower is unobserved. The observed is the cat dead or alive, not both. The observed is the one clock slower, not both clocks slower. The unobserved symmetric time dilation collapses to asymmetric time dilation on observation. This is of course not what Einstein said. It may have been what he meant, but making this change to try to fix a problem that symmetric time dilation makes no sense is of course moving the goalposts, but probably a necessary moving goalpost fix. So let's now look at an article in New Scientist. This is a New Scientist article. Will we ever unite physics? Clocks and superposition could offer clues. Physicists have long sought to marry general relativity and quantum mechanics. Now some reckon experiments that probe the way each theory treats time could finally make it happen. The article goes on to say, physics has a problem. In general relativity, time is entwined with space. It is relative depending on speed or gravity. In quantum mechanics, however, time is an absolute. It is a smooth background into which we can plug our equations. How can time be these two conflicting things at once? And it goes on to say other things. Lots of research aims to tackle this problem. Some treat quantum systems as relative, as in general relativity, while others view space-time as a quantum field, the fundamental entity that everything is made of in quantum mechanics. Now a new approach is gaining interest. It is inspired by the famous Schrodinger's cat thought experiment, in which an unlucky cat feline is trapped in a box, appearing to be both dead and alive. We know particles can be in a state of superposition, appearing to occupy many states at the same time until we measure them. What if those particles could act like a clock? So a quantum entity can act like a superposition of states until it's observed. Then it collapses into one state, but not in all possible states. It has to collapse into one state when observed. And now they're going to treat clocks the same way. Clocks can be in lots of different states until they are observed. So you've got this problem of unobserved, and then it collapses into what's observed. The article carries on and says this. If a clock can be in a superposition of ticking at different rates, it would indicate that time in quantum mechanics isn't fundamental, but relative to a given clock. The experiment is theoretical, but the pair of people, scientists involved, hope it would be possible in 5 to 10 years. Since gravity would be the only thing connecting the masses, the pair say seeing an entanglement would mean gravity would be a quantum phenomena, giving clues about theories of quantum gravity that would help in relativity and quantum mechanics by linking them. So the article talks about clocks being a superposition of different states, that is in the context of general relativity. What I pointed out should really be doing that for special relativity as well. So both in general and special relativity, the relativity principle should be combined with the superposition principle. Einstein was working from thought experiments. His clocks is being dealt with in the context of relativity, where it's just like the cat in the box, not something in the observed realm. What make it part of the observed realm have the collapse to just the one possibility. A cat dead or alive, not both. One clock slower, not both clocks slower. And that is what you'd get when it's observed. Fins, that's the end of this video. Thank you.